Okay, so this talk builds very much on the previous talk that Dan and Paul did. So they sort of set some high expectations where they kept saying, well, Brian's going to tell you about what this is all useful for. So that's, and as Paul said, the work we've done so far is really kind of scratching the surface. But this talk is about our explorations of some of the really cool things you can do with ConstantDynamic. And I have to say, I think ConstantDynamic is just incredibly powerful. And every time I think I have my head wrapped around all the things it can do, I discover some other thing that it's good for. It's really, so it really has quite a lot of depth. So this talk sort of talks about sort of three different aspects of things that you can do with ConstantDynamic. One of them is the one that Charlie so nicely served up, which is why can't I call invokedynamic or ConstantDynamic from Java code? So I'm going to talk about that. I'm going to talk about what a language compiler can do having ConstantDynamic as a translation target. And then I'm going to talk a little bit about things that libraries can do to make them to communicate to a compiler how they use constants and how they can be optimized as a result. So there's a bunch of cool things here. I'm going to go really fast, so I hope I don't lose too many of you. This is all joint work I did with Vicente. Where's Vicente? Just stand up. Okay, stand up and be recognized. So Vicente did all the compiler work for the stuff that I'm going to talk about. So I don't want to take credit for his work, but we had a lot of fun doing this. So, okay, safe harbor slide, we know that. Okay, so constants. Compilers love constants. Constant expressions can be evaluated at compile time. We call that constant folding. You can take things known to be constants and plug those into other expressions as an optimization. We call that constant propagation. And we can use constants at compile time to do control flow optimizations. If you see some code that says if condition and the condition is known to compile to the constant false, you can prune away all that dead code, never generate code for it. So compilers love constants, and the JVM loves constants. The constant pool is an essential part of the JVM architecture. So all the operands for all the bytecodes are stored in the constant pool. So these are things that are strings, numbers, and symbolic references to things like classes, fields, methods, method handles, etc. And constants get resolved lazily, so that's an advantage in startup. They get cached by the JVM, and they can be shared. If you have the same constant that occurs twice in the same compilation unit, you can just have one entry in the constant pool and multiple places that reference it, and that means that the resolution overhead is spread out over all of the uses. And then, of course, the JIT uses constantness to do all sorts of optimizations. So constantness is a really powerful thing. So it stands to reason that if constants are good, more constants is better. And that's kind of the essence of the ConstantDynamic work, which is giving us more ways to express interesting constants in the class file. So as Dan mentioned, we have a new constant pool form, ConstantDynamic, which has a bootstrap method, just like invokedynamic, and a static argument list, just like invokedynamic. But unlike invokedynamic, the arguments the ConstantDynamic composes. You can have a ConstantDynamic whose arguments are other dynamic constants. And so you can express much richer structures in the constant pool using ConstantDynamic than the equivalent tricks with Indy. And so this is really powerful. As Dan mentioned, it's also a little bit dangerous in that you can write bootstraps for things that aren't actually constants, and much hilarity can ensue. And the constants defined with ConstantDynamic are first-class constants in the VM. All of the same tricks that the VM does with lazy initialization and caching and sharing within a class, those all apply to ConstantDynamic as well. And the more constants we have in the constant pool, the more work we can move from invocation time to link time, so that's better startup. And it's also more constants for the JIT to chew on. So, lots of really good opportunities here for improvement. So to turn to the question that Charlie raised in his talk, it kind of stinks that there's no way to write some Java code that reliably compiles down to an invokedynamic. And now that we've added ConstantDynamic, it stinks even more because now there's two things you can't do. So historically, we looked at this as a tool for compiler writers, but, and it is fun to be a compiler writer, but it's not fair for us to hog all the fun. So let's think about how we would expose this in Java. So you could imagine the way we would expose, ConstantDynamic in Java is you'd have some kind of magic method, like maybe called LDC, and you'd be able to invoke it, and the compiler would recognize that some magic has to happen. So let's kind of go with that, pull on that string, see where it leads. What would the arguments to such a magic method look like? Well, they themselves would have to be compile time constants, because the compiler would have to be able to mine the constant info out of your source program in order to write those constants into the class file that it's generating. And so that means that in order to be able to write a magic method like this, we have to have a more refined notion of what it means to be a compile time constant. So there's a little bit of a snake swallowing its own tail here going on, and so let's look at how we resolve that. There are some constants that, constant types that we know about, like string and class, that correspond to literals in the Java language. We have string literals and class literals. So that seems like a good start. If I'm passing string literals or class literals to some magic-looking method, it seems like I should be able to translate those into constants in the constant pool pretty easily. But once you get past that, you start to get into some uncomfortable questions about, well, what do we do about method handles? And what if I want to describe a constant method handle and the class that method is in is not on the compile time class path? We've seen this problem before. Pretty much everybody who's ever written a JLink plugin or a program that generates bytecode using ASM has run into the problem of you can't represent, you're talking about classes that haven't been loaded. Maybe it's because you haven't even written the class files out for them yet, or maybe you just can't find them, or maybe you just don't want to load them. So it points to a more general problem, which is we want to have a way to describe constants nominally and not in terms of things like class. So using a class to describe a class is not always a good choice. It means you have to load the class. That means you have to find the class. Maybe that class isn't accessible to you. Maybe it doesn't exist yet. And maybe you just don't want to take the side effects that loading a class would entail. So we need a better way of describing constants nominally. And this is a kind of cross-cutting concern that I think most of the people in this room have felt the pain of. If you look at the sort of contortions that ASM has to go through, every time we add a new constant pool form, ASM has to write a new class like handle or ConstantDynamic to describe it. And every bytecode framework has to do that. And every compiler plugin framework has to do that. And the JLink framework has to do that. And the constant pool is a fundamental part of the Java platform. We should have a way of talking about the constant pool more directly. So these are problems that show up everywhere, and so it seemed like a problem worth solving once and for all because it shows up with bytecode APIs, it shows up with indie bootstraps that generate bytecode, it shows up in JLink transforms, it shows up in compiler plugins like annotation processors. So it seems kind of an obvious thing, let's have an API to describe constants. And it's not a particularly hard API to write, right? It's just a bunch of little wrapper classes around bundles of strings and things like that. So, okay, we can do that. So I'm going to walk you through this API that we've designed, and then I'll show off the more interesting things of how we've actually used that. So we start with a basic interface called ConstantDesc. So it's a nominal descriptor for a constant. It's a value-based class, so it's an immutable class. And if you want, there's a way to resolve it to a live object, but you need to supply a context for things like class loading and access control. And conveniently, we have a mechanism for that called lookup. We have this interface, ConstantDesc. It's got a resolution method. You pass it a lookup, and it gives you back an object, or maybe it throws an exception. And then we have a bunch of classes that implement this interface. So like ClassDesc is a descriptor for a class, and it implements ConstantDesc that resolves to a class. Straightforward enough. Everybody could write this API. It's not hard. So the types in the constant pool, as per JVMS 5.4, are strings, numbers, classes, method types, method handles, and now ConstantDynamic. So we'll need a subtype of constant desc for each of those things. Conveniently, strings and integers and such can be their own descriptors. They're already nominal, so we don't need to have a string descriptor and an int descriptor. Integer and string will do just fine. And so we've just retrofitted string extends constant descriptor, integer extends constant descriptor, and we're all done there. And for the rest, we've just written classes to describe them. So class descriptor, method type descriptor, method handle descriptor, and we wrote a bunch of simple factory methods and combinators for making them. So give me a class descriptor for the class whose name is this, or the class whose descriptor string is this, or a method type descriptor for this list, for this class desk for a return type, and these class desks for parameter types. And so you see how the higher level abstractions build on the lower level ones. If you look at the factory for a method handle desk, it takes a class desk to describe the owner and a method type desk to describe the signature. But it's all fairly straightforward. So, and then at the top of the stack here, we have some nominal descriptors for dynamic constants and for indicites. And these are, again, very simple wrappers, right? So what do you need to describe an indicite? You need a method handle descriptor for the bootstrap. You need a name and a type. The name is a string. The type is a method type. And what are the arguments? Well, the arguments had better be compile time constants. They better be, and so we can describe those with constant descriptor. And so we have, so we have a way of describing both a condi and an indi nominally. Okay, so again, no magic here. If you look at the code for these classes, it's all just the obvious factory methods and a few convenience accessors for shuffling the parts around. Okay, so keeping score here, we have here are all the subtypes of constant desc. There's the string and number types that are built in. There's the descriptors for class, method type, method handle, and dynamic constant. And if you're writing an API, say that manipulates bytecode, you can treat this as an exhaustive list. So you can, for example, have a method for generating an LDC. It takes a constant descriptor, and it's going to be one of these types, and you can case off these types, and they map one-to-one to the constant pool forms that are defined in the JVMS. So perfectly straightforward. Okay, getting back to our real question of what does our LDC method look like? Well, now we're able to give an answer. So we need a way to describe the constant, and we have one constant descriptor. So we picked a random name. Intrinsics might change. And there are two methods on it, LDC and invokedynamic, named after the bytecodes they emulate. And what does LDC take? It takes a constant descriptor, and that's it. And similarly, the invokedynamic method takes a descriptor for the call site and the list of dynamic arguments. And the compiler should be able to, we hope, we'll see how that works, be able to look at this and say, yes, that's a valid description of, nominal description of a load constant. I know how to turn this into a real LDC instruction, and if you try to call it reflectively, well, it fails because this is support code for the compiler, not for the runtime. So Dan showed you an example of using the new primitive class bootstrap. So let's look at an example of the same thing. Let's use this to load int.class as a constant. So we have the bootstrap, constant bootstrap's primitive class. We need to make a dynamic constant descriptor to describe that, and then pass it to LDC. So, well, first in order to make a dynamic constant descriptor, we have to have a method handle descriptor. In order to make a method handle descriptor, we have to make a method type descriptor. So, okay, we do that. We make a method type descriptor of something that returns class and takes the usual three arguments, lookup, string, and class. And we pass that to the constructor, the factory for method handle descriptor, where we say I want a method handle descriptor for the static method, whose owning class is constant bootstraps, and whose name is primitive class, and whose type is that method type I just made. And then we wrap that with a dynamic constant descriptor and the name and type arguments, and we pass that to intrinsics LDC. And that looks like kind of a lot of code to do something very simple, so this is where the magic comes in. So The compiler is supposed to look at that code and grovel through all of that stuff and say, okay, I know how to pick out all the little nominal bits that are going to go into my constant pool, and so I'm going to find them in the program. I hope they're all compile time constants, because we have problems otherwise. And I'm going to stuff them into the constant pool, and then I'm going to intrinsify the LDC call and generate an LDC. So everything that arrives at that intrinsification point, that LDC method, had better be a compile time constant. So what do we have to teach a compiler in order to be able to do this trick that I just described? Well, we have to teach it how to take apart these descriptors. That's easy, because these classes are really dumb. We have to teach it how to tell whether one of these descriptors is a compile time constant or not. And we want that to work even when we have a dynamic constant descriptor that refers to a method handle descriptor, that refers to a method type descriptor, that refers to class descriptors, that refers to strings. In other words, it has to be constants all the way down. So we have to teach the compiler about that. Now, the compiler already does some rudimentary compile time constant folding. If you say A plus B, the compiler will squash them into the string AB. So let's build on this, and we'll define what we call an intrinsifiable constant expression. And we teach the compiler to have this more sophisticated notion of constant expression. And we define this by induction, and it's really obvious what we're going to do. So all of the existing literal types, like numeric literals and string literals and enum literals, well, those are going to be intrinsifiable constants. And then things that add together to intrinsifiable constants should be an intrinsifiable constant. And then here's where we kind of depart from the constant folding that we do today. We also say, if you have a reference to a static field in the same compilation unit whose initializer, static final field, whose initializer is also an intrinsifiable constant, then the reference is a constant as well. And similarly, if x is an effectively final local, a reference to, and its initializer is a constant, then the reference to the local should be a constant too. So this gives us some static typing rules that allow us to say whether or not a given program, when an expression arrives at an intrinsification point, whether or not it could possibly be an intrinsifiable constant or not. So that's a good start, but it's actually not enough. We have to do a little bit more, because if you look back at the code, which I'll show you again in a few minutes, we also had to call some methods. We had to call class descriptor of. And we want that to be a constant too. So we have to tell the compiler that some methods are safe to invoke reflectively at compile time. And so let's call this kind of method a constant factory. And these have to have all the obvious characteristics. They have to be pure functions. They have to be side effect free. And what we can teach the compiler is, if you know a method is a constant factory, and you know all its arguments are intrinsifiable constants, and you can actually call the thing reflectively at compile time, then the result will be a constant too. So we teach the compiler this, and we teach the compiler that those factory methods, class descriptor of and method type descriptor of, are constant factories. And then we add a new rule to our set of what it is to be a constant, which is, if all the arguments, and maybe the receiver too, of a constant factory method invocation are all constants, then the invocation is a constant too. And we do the same thing for static fields. So that actually was a pretty straightforward application of well-known compiler constant folding. We just had to be able to teach the compiler how to recognize which methods, and right now we do with an annotation. I'm not sure how it will work in the final version, but it's pretty straightforward. So okay, so now this is the same code I showed you before. Is this invocation going to be an intrinsifiable constant? Well, if you follow through all of that, we have a bunch of references to static final fields, and then invocations of methods with those references to static final fields. So this type thing, that's a constant. And, well, primitive class, that's a string, that's a constant. And I have some enums, and that's a constant. And another reference to a field, that's a constant. So this bootstrap method descriptor, that's also a constant. And you follow this all the way down, you apply all the rules, and you say, yes, the thing that I'm that I'm passing to intrinsics LDC, that's an intrinsifiable constant, so I should be able to generate the bytecode. But we're not quite there yet. We have to do a little bit more work. We also need to teach the compiler how to evaluate these intrinsifiable constant expressions, and that turns out to be really straightforward. So we define this partial function on expressions called TC for tracked constant, and you define it in just the completely obvious way, right? So TC of E for a string literal is the string. TC of E for where E is A plus B is the obvious thing. The compiler already knows how to do that. And then we define rules for things like enums, and as long as the enum can be loaded at compile time, that's straightforward. And for method invocations, well, we reflectively call the method with the tracked constants for all the arguments. And if that doesn't throw an exception, then we say, okay, that's the tracked constant for that invocation expression. To this, we add a straightforward dose of constant propagation, where if you have a later expression that references a known intrinsifiable constant, we can replace that sub-expression with an LDC and propagate the constant forward. And as we go, what we do is we just, for any expression that we think is intrinsifiable, we compute the expression, we staple it to the tree in the compiler, and maybe it will be useful later, maybe it won't. We haven't done anything with it yet. So now we're actually ready to do the thing that Charlie wants, which is to intrinsify this LDC to an LDC. So we do all of our constant folding and propagation to push all the constants to that intrinsification point. The compiler sees that the thing at the bottom is a tracked constant, and it's of type constant desc, and it's actually evaluated it at compile time, so it has its hands on one of those. And now all it needs to do is take that thing apart, and it knows how to do that because I had that slide about 10 slides back where I said, here are all the subtypes we know, here are all the constant pool forms, look, a nice one-to-one mapping, that's about half a page of code for a compiler to intrinsify that, and the compiler can generate an appropriate constant pool entry and emit an LDC that refers to it. So that's pretty cool. And there was really not a lot of rocket science here. It was just applying well-known techniques. So here's the bytecode it generates. Well, that's kind of sad. You can see way at the bottom in the really small type in red, the LDC we wanted. So yay. And then a whole lot of garbage that we didn't want. So what's that garbage? Well, the garbage is the translation of class descriptor.of and method type descriptor.of and all of this setup code we had that was really only there to feed the intrinsic point. But we have a way out, right? We know, so this code is useless, and we would like to be able to dead code eliminate it because it served its purpose. It told the compiler what we needed to know to generate the code we want. But it left us with a lot of dead code. But we know that the constant factory methods were side effect free. We said that they were. So if the compiler can tell that the results of these things are actually dead, which it can, because that's what compilers do, we should be able to dead code eliminate that. And that turns out to be pretty straightforward. It's easy for me to say because Vicente did all the work. But from my perspective, this is really straightforward. You put a bunch of stuff on the slides and it happens. And this is the code that we get out, which is actually the code we wanted, right? So all that's in there is a single LDC, and it points to a bootstrap method entry whose bootstrap is the primitive class bootstrap that Dan gave an example of earlier. And there we are, okay? So that's really cool. All right, so that's great for intrinsification. That, like I said, I'm going to talk about 3 things, so I've just checked off one of them. What else can we do with this? Let's take stock of what we've done so far. We created a constants API in the JDK, which is generally useful. We taught the compiler how to turn a constant descriptor into a constant pool entry. That seemed pretty useful. We taught the compiler, in order to make intrinsification work, we had to teach the compiler about constant folding and constant propagation, which are general optimizations that must be useful for something else. And we taught the compiler about some dead code elimination, which also seems pretty useful. So hopefully we're not done here. And so far we're able to track these constants through locals and through fields and intrinsify, invoke dynamic and load constant, and then eliminate all the scaffolding from the generated code. So we're doing pretty well, but I'm greedy and I want more. Here's a nice little bonus that sort of surprised us because it came out for free. If you know how lambdas are translated, when a lambda captures something, we translate it using a more expensive translation story. And very often, the captured variables are constants. So here's an example where we have a prefix constant and we have a lambda that just concatenates that prefix onto its argument. And in a JDK today, this gets translated with Indy as a capturing lambda, but it doesn't really have to be a capturing lambda. And as soon as we turned on constant propagation, it propagated that constant right into the desugared lambda method and turned this into a non-capturing lambda, which enabled us to translate it using condi. And that just sort of happened for free without us noticing it, which was a nice hint that these generic optimizations interact with each other in nice ways. The way this used to get translated is with invokedynamic, and this turned into translating with condi, where we just say LDC of this function, and it's just a constant function, and it gets inlined really nicely. So that turned out to be a nice bonus. But let me talk about the other thing about I wanted to talk about, which is how can we write libraries to take advantage of this kind of constant awareness on the part of the compiler. So what if we did everything we did in the previous example, but we didn't intrinsify it, we actually used it as an argument for something else. So here we have the same two lines where we make a method type descriptor, we make a method handle descriptor, and instead of intrinsifying it, we pass it to system out print line. So we'd like to be able to do something there too, and we've already done all of this work to prove that these things are effectively compile time constants, so we should be able to optimize this even in the absence of intrinsification. So without anything special, here's the code that we generate for that. So there's a lot of byte code for call the factory for method type descriptor, call the factory for method handle descriptor, and then pass it to print line. So those are the three red things, and the rest is all just setting up the calls. But we should be able to do better here. So these are all invocations of constant factory methods with constant arguments. These descriptors are all value-based classes. These descriptors are all things that can be described in the constant pool. So we would like to just do that. We would like to LDC something and pass that to system out print line. So how do we do that? Well, we need to know how to convert those tracked constants back into constant pool entries. But not all tracked constants can be converted into constant pool entries. So we need a little bit of help from the classes that describe these trackable constants to be able to say, oh yes, I'm an object, but I know how to describe myself in the constant pool. And if we do that, then that will enable us to more aggressively constantize things at compile time. So to do that, we have to define one new type, the amusingly named constable type, which means able to be a constant, of course. And it has one method, which is describe yourself. And in what form do you describe yourself? Well, with a constant descriptor, of course. And it's a partial method, so it returns an optional. Maybe it says, no, I can't describe myself. Just generate some bytecode. Do what you're going to do before. But maybe it will come back and say, oh yes, I'm this thing that can be described by this constant descriptor. And then we retrofitted that interface onto class and method type and method handle and var handle and enum and all of the things that are morally constants, in the JDK, and onto the descriptor classes because those are constants too. And so you can ask one of these instances, describe yourself as a constant desc, and maybe they can, in which case they're suitable for turning into LDCs. And if they say no, I can't describe myself, then fine, you just generate some bytecode. And so the compiler will track constants for all of these intrinsifiable constant expressions. And when we get to code generation time, this is sort of the last trick we had to teach the compiler, when we get to a node for an expression and that expression has a tracked constant, we then look at that constant and say, oh, do you implement constable? All right, try describing yourself. And if it comes back and says, well, yes, I'm describable by this thing, then instead of generating bytecode for that whole tree, we generate an LDC for the constant that the thing described itself as. And so if the compiler is able to fold all of these calls into constants and they're not dead, it will generate just an LDC for them. So here's the code, same code as before. Make me a method type descriptor, make me a method handle descriptor, and then print it. And when we translate it, this is what we get. We say, get me the print stream, do a load constant of this method handle descriptor, and invoke the print line method on it. And all that other gunk just went away because it got evaluated at compile time. It got turned into a description of a constant at compile time. Everyone agreed, yes, this constant is, this is a good description for this constant. And so the compiler just said, well, if it's a constant, I'm just going to generate an LDC for it. 50 lines of bytecode got compressed down into 3 or 4. And because ConstantDynamic composes with itself, more complicated examples will fold together very nicely. So, you can look at that and say, where'd the code go, right? And it's the same place, it fell victim to, 50-year-old compiler tricks, constant folding, constant propagation, where the compiler was able to figure out everything in this program was a constant. I combined smaller constants into bigger constants. I tracked and propagated them throughout the program to the point where they were used. I had to emit bytecode for them. I said, can you describe yourself nominally? The thing said yes. And, everything else was eliminated as dead code. So, small number of tricks that work together really nicely. So you might ask, what did method handle descriptor do to achieve this? Well, it had to implement one method. It had to implement describe constable. And that method has to hand back an optional of a constant descriptor. And what kind of constant descriptor is it going to hand back? Well, a descriptor for a dynamic constant, because it's not a built-in kind of constant. It's not a string. It's not a class. It's not a method handle. I wrote 4 or 5 lines of code to say, okay, well, make me a dynamic constant descriptor to describe the result of invoking this bootstrap with these arguments. I had to write that bootstrap, which was another 6 lines of code, and I was done. So this is kind of the bonus round. So it actually gets even cooler than that, and this is my favorite part of it. I hope the explanation comes through. So we talked about how the compiler is able to see through these nests of constants, turn them into something that can be described in the constant pool, and turning those into loads. It turns out that if you have, say, a builder kind of API, it can actually, when you say, give me a builder, give me a sandwich builder with cheese, with mustard, with turkey, with roast beef, and now build. You took a kind of circuitous path to describe that sandwich. First, you started with an empty builder, and then you had the builder with cheese, and the builder with cheese and mustard, and the builder with cheese and mustard and roast beef. And that was like a lot of steps to describe the building of your sandwich. We would rather not actually emit all that bytecode. We would rather emit a constant that describes the sandwich that has all of those things on it. So here's an example using the constant descriptor API that does this. I say, give me a class descriptor for Java lang string, and it makes an object that is the class descriptor for Java lang string. And then I ask that object, give me a class descriptor for the class that is an array of whatever you are. And it makes another class descriptor for array of string. So now I have 2 class descriptors in memory, one for string, one for array of string, and then I go ahead and use the array one. I didn't really want the first one. I only made it so that I could get the array one out of it. So if I just generated straightforward bytecode from this program, I'd get some code to call the factory for class descriptor for string, and then I would use that to make a class descriptor for array of string. But really, I just want to go straight to array of string. And this framework that I've described actually does that in one go. Because when you take the class descriptor for array of string and you say describe yourself, it doesn't have to reconstruct the path by which it was described. It only has to reconstruct its final state. So when I translate this program, when I compile this program, this is the bytecode that comes out. There's one LDC for a class desc, and if you look at the bootstrap method table for it, you see it is I'm calling the bootstrap for class descriptor, and its sole argument is a type descriptor, and the type descriptor at the bottom is the type descriptor for array of string. So I wrote the code in a way that was readable to humans. Start with descriptor of string and then make an array out of it. And the compiler folded it together and went straight to the final answer that I wanted and put that in the constant pool and garbage collected all of the rest. Okay, so if you write your libraries carefully using this mechanism, you can write library idioms like these constant descriptors that expose concepts that are natural to the user, that can be written in a very natural way, and then at compile time, it all gets folded down to the actual thing you want, and everything else gets thrown away. So that's really cool. And I see Gary is nodding, so at least one person followed that example, so I'm happy. So let me summarize what we've done. A few new abstractions. Constant descriptor describes a loadable constant pool entry. Constable describes a live constant, like a Java lang class. And these two things are kind of duals of each other. The constant descriptor can be resolved into a live object, and a suitable live object can describe itself with a constant descriptor. And then we have these methods and fields that are tagged as constant factories, and those are things that are safe to evaluate reflectively at compile time. That comes with restrictions, and it only bothers to do that if the arguments themselves are also constants. And a constant factory might yield a constable, it might not. It might be that you have a builder where the builder isn't constable, but the built thing is. So you have builder dot with this, dot with that, dot with that, and that whole chain of things is not constable, but the thing at the end is. And that's what allows you to go right to the destination. And then we taught the compiler how to aggressively evaluate through these methods to expose the constants, and then apply the standard tricks of folding, propagation, intrinsification, constantization to generate better bytecode. So that's really cool. And as Paul said, we're just scratching the surface here. This is just sort of our initial proof of concept that this stuff is useful. We expect we will find more and more ways to use this in the compiler and in the libraries to allow people to write code that feels natural and is type checkable and is safe, but then compiles down to very tight bytecode. So obvious things we can do: have more constant bootstraps in the JDK, more constable methods in the JDK, more constable classes in the JDK, and the more things that are tagged this way, the more things that these optimizations will have to chew on. Gives the JIT more constants to work with, less bytecode means faster startup, more laziness. These things all work together to get really nice results. So that's it for my talk today. I know I talked really fast. I did make it within the time window. We have about 5 minutes left for questions. I'm happy to take questions. Martin.